Hello, this is Justin Campbell again. Thank you for dropping in. I would assume that you watched the first video and that it piqued your interest. This video will be the second in a series of videos aimed to provide science enthusiasts with information on the utility of cloud computing within the scope of building and running climate models. In this deliverable, I will provide you first with a recap of the product design process and the project objectives. Feel free to skip these sections if you're not in need of a recap. From here, a discussion of design requirements and requirements gathering will be provided before moving on to the final and most important topic of this deliverable, namely a presentation of high-level product designs for the distributed systems that aim to satisfy the SMART and stretch goals discussed in the project objectives. So I wanted to provide a refresher on the design process methodology that I've incorporated into this project. This methodology is broken down into 6 phases shown in the schematic. Having begun incorporating feedback from project collaborators on requirements and design ideas into my product system designs, I'm currently progressing through the understand and ideate phases to develop the framework of my product design before translating that software application, architecture agnostic product design into working preliminary designs that will be tested in the next steps, itemize and evaluate phase. So the next thing I wanted to do is briefly recap the project's objectives. As a refresher, the product objectives are broken up into 2 categories. First, SMART goals that are specific, measurable, achievable, and time sensitive that will serve as a baseline for end project goals. And secondly, stretch goals that add complexity or introduce new features to product design that require additional research, time, and collaboration. The SMART goals are to develop portable units of software, ideally containers that can be leveraged to build and run computationally inexpensive MIT GCM model problems with installation of MIT GCM Echo libraries and their dependencies, and without MPI libraries. Secondly, to configure support for these units of software on the most frequently used computing platforms, architectures, and operating systems according to Krios group users, to document working software products and code repository and image registries, and lastly, to present the results to the senior developers that are responsible for merging pull requests into the MIT GCM Echo ecosystems. And then the stretch goals for the project include implementing a graphical user interface for end users to be able to interactively input MIT GCM model problem parameters, compile and runtime parameters and other specifications such as step size, spatial and temporal domain boundaries, along with desired post-processing and data analysis tasks such as invoking Echo library routines to perform certain data analysis on the model output data, such as rendering data visualizations, and ideally rendering the output on a GUI in the containerization environment. Secondly, to scale up support for model problems and Echo visualization tasks to enable more computationally expensive configurations that require more RAM or occupy greater CPU load. Thirdly, to add support for ASTI regional domain model problems. And then lastly, to scale up support for the product to run on the most widely adopted computing platforms, architectures, and operating systems according to more general purpose MIT GCM community use, as opposed to specifically geared towards platforms and architectures that are used by the Krios group. Now, after developing project objectives and determining general frameworks for a product development or design process, development environment workflows, and communication hierarchy, I began documenting project requirements according to feedback received from fellow graduate students and personal knowledge of how to improve the MIT GCM Echo workflow in a distributed system. In particular, the project requirements have and will continue to be documented into 2 parent categories, namely subjective technical requirements often referred to as qualitative requirements, which are those that are interpretive and describe a product or project's requirements at a high level, and quantitative requirements, sometimes merely referred to as technical requirements, which are those that are countable, measurable, and thus ascribed a numerical value for verification. Now, requirements will be continuously updated as they see fit according to time and development environment constraints. Moving on to system design requirements. So since the project's objectives are to release a product that is robust enough to incorporate a majority, if not all, of the tasks in the MIT GCM ECHO workflow, it's reasonable to conceive a system design that divides the workflow tasks across multiple portable units of software or containers to prevent one unit of software from taking on a computationally intensive quantity of tasks that exceed memory allocation, result in slow performance, or crashing, to name a few concerns. This necessitates the need for the containers to communicate the output of these tasks with one another in real time to effectively balance the workflow, which can be accomplished using a container orchestration system. Since both the container technology platform and the container orchestration system will be run on users' host machines, there will be host machine software and hardware requirements that must be met for successful use of these products. Thus, the requirements have been assigned to 3 systems that will be incorporated into the design of the products, namely the container technology system, container orchestration system, and the software stack system. The containerization technology system refers to the open source containerization platform itself, in which the containers will be built, tested, and deployed from. Examples include Docker, CoreOS RKT, and Cloud Foundry, to name a few. The container orchestration system designation is a system in which the containers, databases, and other services / microservices will be developed to communicate in a load balanced distributed system. Lastly, the containerization software stack is a software stack from which the containers, the source code running on the containers, services and microservices, and the communication between them will be built or configured. Then, to expand on what was mentioned previously, the requirements within each system scope we categorize as either subjective technical requirements or quantitative requirements. Now, next, high-level product designs that are used to communicate the intended workflow of the products will be provided in rudimentary flowcharts. These flowcharts provide essentially a sequential order of operations in which the containers, services, and microservices in the product will execute to perform high-level tasks in the MIT GCM or MIT GCM ECHO workflow. More high-level schematics and detailed designs will be provided for both individual systems and the services, microservices in those systems later in the project timeline, once system designs have been down selected from a feasibility analysis. Now shown in the slide is a high-level product design of a containerized distributed system whose behavior is to be consistent with the objectives documented under the aforementioned SMART goals. From the standpoint of the end user, the first step would be to initialize the containerization engine and container orchestration system on the end user's host machine. From here, the end user will be expected to pull containers that are tagged for release from an image registry to a local machine. Then the end user would be expected to run one more command from the user's terminal, namely one that executes a base container, let it be container 1, that prompts the user to input model, compile, and runtime parameters, along with other model configurations such as processor number, temporal spatial domain ranges, time step sizes, etc., through a GUI. And this excluding support for MPI at first due to complexities between MPI libraries that need to be installed both inside and outside of the container on the user's host machine, which can make it kind of messy. From here, the container would build a job scheduling submission script to schedule the model compilation and execution on a job scheduling platform such as Slurm. Then the container orchestration system would spin up a second container to load balance tasks running on instances of the container daemon. Before executing any tasks on the second container, the first container would then relay the job submission script to the second container using a network protocol, and then terminate the first container to load balance tasks running on the container daemons. From here, the job script would be submitted to initialize job scheduling and execution on the compute nodes being leveraged by the host machine's HPC cluster. Then when memory is available, the compute nodes will execute the job script to compile the model and run the executable. The container will then write the standard and error output out to a file for the end user to view. The end user may then run commands inside of the container to write the data out to a custom volume for future reference. They will then be prompted through a GUI to run another model problem. And if they select yes, the second container will be terminated, the first container run for a second time, and the remainder of the procedure will repeat. Otherwise, if the end user decides not to run another model problem, the container daemon will terminate the container, and ultimately the entire distributed system, culminating in the shutdown of the containerization engine. Now, this slide provides a similar flowchart whose elements are slightly amended and more introduced with an intention of satisfying the stretch goals in the project. The first difference between the two designs lies in support for building and running model problems using MPI libraries, as shown in the third element in the leftmost vertical column. Fast forwarding a bit through the elements, after the compute nodes have executed the job to compile and run the executable, the model output would then be relayed to a third container, spun up in the container orchestration system before the system terminates the second container. This third container will use a GUI to prompt the user to select data processing, data analysis methods to execute under the hood to process output data according to subroutines that are defined in Echo Python libraries. This will ideally allow for the system to automate the performance of any analysis technique on the output data that the end user would otherwise be required to learn upon running through the documentation and reproduce manually upon installing and configuring an environment for using Echo libraries on their own host machines. The output of this data processing and analysis task would then be rendered on a GUI inside of the containerized environment if the end user desires, and they shall be given the option to write out the analysis to a volume on the machine, similar to the output, the standard and error output of the model run itself. Lastly, similar to the design of the former product, the end user will be prompted with a message to run another model problem. And if they select yes, the procedure would again repeat. Otherwise, the distributed system would be terminated. Now, the next steps in the project timeline will involve continuing the documentation of product design requirements according to subjective technical requirements and quantitative requirements for each system in the product design, namely the container technology system, container orchestration system, and product software stack systems. Preliminary designs for each system will be researched and documented. And for this particular project, the preliminary designs for the container technology and container orchestration systems will refer to open source products that have already been developed, but whose application to this project need be studied. For example, Docker, CoreOS, ArcAT, Cloud Foundry with respect to the former, and for the latter, examples will include Docker Compose, Docker Swarm, and Kubernetes. With respect to the software stacks for the two product releases, the preliminary designs may be incorporated into the project lifecycle after a suitable container orchestration technology system and suitable container orchestration and container technology system have been incorporated into the developer's workflow. The potential delay stems from the developer's interest in determining and getting comfortable with the computational constraints of developing and testing source code using these systems. There may be limitations to translating certain high-level design preferences for the software stack into these development environments, such as the environment not being compatible with like graphical user interfaces or memory load balance restrictions when attempting to run intensive code that satisfies certain stretch objectives. This will need to be examined moving forward before a decision is made. Thirdly, once these preliminary designs have been set aside, strengths and weaknesses of these designs will be documented, and the designs will be checked against requirements. And then from here, a feasibility analysis tool will be developed to down select a design for both the container technology and container orchestration system that is optimal according to the most critical requirements and desirable project objectives. This will also be accompanied by a decision matrix and trade-off schematics to weigh conflicting attributes of the designs. And here are the references. Thanks for tuning in.